All right, so you can see in this box here we have these conversion formulas for rectangular to polar and polar to rectangular. It's these four equations relating the r's and thetas in polar coordinates to the x's and y's in rectangular or Cartesian coordinates. What I'd like to do really quickly is show where these come from and then practice using them. These conversion formulas are really, really important. You're going to want to have these memorized. And just to kind of give you a sense of their importance, so moving on from this class, you're going to go into Calculus 1. You're not really going to use polar coordinates at all in Calculus 1, unless you unless your instructor comes up with some sort of unusual example. So like a couple of topics, it's going to seem like some of the things that we cover in this class weren't actually needed for calculus, but the reason for that is because they become really important in Calculus 2 and Calculus 3. Calculus 2 and Calculus 3 make extensive use of polar coordinates, so it's really important that you have these memorized, and it'll naturally happen as we go through homework problems and practice using them. But I just wanted to emphasize that. So to come up with those, I'm going to use this little space up here. Let's suppose we have a point somewhere in the plane. I'm going to put it right here. And that point can either be measured in rectangular coordinates, x, y, or polar coordinates, r, theta. So I can create a diagram like we had on the first page showing what all of those coordinates represent. X would be the base of this right triangle, y is the height, theta is this angle, and r would be that hypotenuse right there. One of these formulas, this one down here, is pretty much immediate from this diagram. R squared equals x squared plus y squared. That's just the Pythagorean theorem with this right triangle right here. So you can see this relationship right away. Also, this second one is pretty immediate as well, because here's theta. If I took tangent of theta, that's opposite over adjacent. So I can see that tangent of theta in this case should be y over x. It's pretty much automatic. But what about these top two? Well, let's start with the x. So I notice that it's using a cosine of theta here. If I were to find the cosine of theta, thinking of this as a right triangle, cosine of theta is equal to adjacent over hypotenuse. That's x over r. But notice, if I were to just multiply both sides of this by r, and maybe switch the sides that things are showing up on, sides of the equal sign, I get x equals r cosine of theta. That's where this one comes from. A similar derivation shows that y is equal to r sine of theta if I were just to set up sine of theta equals y over r and then solve for y. So these are easy to derive just from that picture, but we should practice using them. So we're going to start by converting some points between the two coordinate systems. Let's suppose we have this point here, 6, 5 pi over 3. Right now it's in polar coordinates, but what I want to do is convert it to rectangular coordinates or Cartesian coordinates. That's where these come into play. Rectangular coordinates are the x and the y. I know the r and the theta. They can be plugged in for the r and theta in each of these formulas to produce the x and y. So starting with x is equal to r, which is 6, cosine of theta, cosine of 5 pi over 3. Okay? 6. So 5 pi over 3, that's in the fourth quadrant. I know cosine of 5 pi over 3 should be 1/2. So I get an x coordinate of 3. Use the conversion formula for the y next. So y will equal r, which is 6, sine of theta, which is 5 pi over 3. This comes out to 6 times negative root 3 over 2. That's what sine of 5 pi over 3 would be. Do a little simplifying here. This comes out to negative 3 root 3. So in rectangular coordinates, the point 5 pi over 3 becomes the point 3 negative 3 root 3. Okay? Just a matter of plugging things in. Down here, we're going the other direction. We're converting the points shown here from rectangular to polar now. So these are rectangular coordinates, but I want to represent them using polar. I'm giving you 3 examples here because they illustrate kind of 3 different cases that we can encounter. These 2 in particular are what are going to give people some trouble. So let's start with this one. To convert these, I'm going to be using these other 2 conversion formulas. R squared equals x squared plus y squared. Tangent of theta equals y over x. So let me start with r squared. R squared is going to equal root 6 squared plus root 2 squared, which would be 6 plus 2, or 8. Taking square roots of both sides is going to give me r equals the square root of 8, which you can simplify to 2 root 2. Okay. Next step, I want to find theta, the angle. So I'm going to use this conversion formula up here. Tangent of theta is y over x. Okay. Tangent of theta equals y over x. That's root 2 over root 6. Now, the way this appears right now, it doesn't look all that familiar. It doesn't look like an angle that or a value that we represent as the tangent of something, but I'm going to try to simplify this a bit. So we have a property of radicals that says if I have a radical over a radical, I can think of that as the square root, in this case, of 2 over 6. Okay, this becomes 1/3, which is the same thing as 1 over root 3, and if you rationalize that, you get root 3 over 3. That does look familiar to me. So this, I know, can be a couple of possibilities. Theta could either equal pi over 6, because I know that tangent of pi over 6 is root 3 over 3. But it could also equal 7 pi over 6, because 7 pi over 6 is in the 3rd quadrant, and tangent of 7 pi over 6 would also be positive root 3 over 3. So I have to determine which of those 2 angles is the one that I want to use. One is correct and the other one is not. The way I make that determination is I go back to the original point in rectangular coordinates and I think, what quadrant does this belong to? Well, the x and the y coordinates are both positive. This would mean that we're in the 1st quadrant. So 7 pi over 6 would not be correct. 7 pi over 6 is in the 3rd quadrant. That means the angle I'm looking for is pi over 6. So notice that we have to kind of go back to the original point and sort of think through which of the 2 possible angles is the correct one. Okay, putting these together in polar coordinates, we have the point 2 root 2, pi over 6. So this is the 1st point. Okay. Now let's try the next point. We're working with -5, -5. All right, so same idea. I want to find r, and to do that I use r squared equals -5 squared plus -5 squared. That would be 25 plus 25, or 50. So that r is the square root of 50, which is equal to 5 root 2. Okay. Next up, we want theta. So I do the same thing as before. Tangent of theta is equal to -5. That's y over -5, which is x. This comes out to 1. So I want to determine, where is tangent of theta equal to 1? Well, there's 2 places. In the 1st quadrant, tangent will be positive, and it's equal to 1 when theta is pi over 4. In the 3rd quadrant, tangent is also positive, and we would get a value of 1 if we did tangent of 5 pi over 4. So it's one of those 2. If I go back to the original point, -5, -5, x and y are both negative in the 3rd quadrant. So that narrows it down to 5 pi over 4. And I want to point something out about this one. It's tempting when looking at this, tangent of theta equals 1, to solve this with an inverse tangent. Because normally you would think, okay, I'm going to try to get theta by itself. If I take inverse tangent of both sides, then theta will be isolated over here, and then I just have the inverse tangent of 1 over here. The problem with that is the inverse tangent function has a range that's restricted to the first and fourth quadrants, which we've discussed before. You notice it'll never give you solutions in the third or second quadrant. That means it can give you wrong answers if you just blindly take an inverse tangent. So that's why we do this process. You know, you think through which of the two possible angles would make the most sense. Notice if I did take the inverse tangent of 1, then this would tell me that theta is equal to pi over 4, which is the wrong angle. So this means the polar coordinates of the point we are interested in is 5 root 2, 5 pi over 4. Okay. And again, this same point can be represented in an infinite number of different ways, but this is the most direct representation. Okay, finally, we're going to be working with this point right here. Now, this point, 0, 12, I know right away that r would be 12. I'm going to go through the derivation, but through using the formula, but I'm also going to tell you why I know without even using the formula that it should just be 12. So r squared is equal to x squared, which is 0 squared, plus y squared, which is 12 squared, which is equal to 144. Therefore, r would be the square root of 144, which is 12, like we said, right? I'm going to come back to that in a second, and I'll show you why we don't really need the formula for this specific case. Here, we run into a bit of a problem, though, when I'm finding theta. Because if I'm going to do theta, I'm going to be using this. Tangent of theta equals y over x, 12 over 0. Well, that's undefined. Okay? So that sort of leaves me in a pickle. But that's okay, because we actually know from our tangent function, there are a couple of places on the unit circle where tangent is normally undefined. It happens when theta is either pi over 2 or 3 pi over 2. So rather than try and deal with this thing directly, I'm going to look at where the point 0, 12 would be if I plotted it in rectangular coordinates. Okay, that would actually be right here. There's the point 0, 12. I can see pretty clearly that creates a right angle with the positive x-axis, or the polar axis if I'm thinking in polar coordinates. So that would mean that my angle is pi over 2, which again is one of the places where tangent is undefined. Similarly, I can see right away that the distance between that point and the origin is 12, which is what r represents. When one of your rectangular coordinates is 0, like in this case, that means that this point lies on either your x or y axis, depending on which coordinate was 0. When the point lies on the axis, this is just a straight vertical or horizontal line. If the point lies on either axis, the distance between that point and the origin is just a straight horizontal or vertical line, which you can very easily see what that length is. So taking all of this and putting it into our polar coordinates now, we have 12 pi over 2 as our polar coordinates for that point. Okay? All right. Let's go ahead and move on to... Actually, you know what? I think the next couple of examples I'm going to save for the next video.